look at Chapter 2, Section 2.2 and 2.3 today. 2.1 is just an introduction, so there's really nothing that we need to do with that, so you don't need to worry about it. So Section 2.2 is on Ohm's Law. Ohm's Law. And again, if you've taken physics, you've seen Ohm's Law already. So Ohm's Law simply says V equals IR. That says that our voltage is equal to our current times resistance. Or that 1 volt equals 1 amp times 1 ohm. So resistance is measured in ohms. And we can calculate resistance of any material. So if we have some tube of material here, and we'll say that it has an area A and a length L, then resistance R is equal to rho, the resistivity. That's a property of the material. You have to look up a table and see what that value is, times L over A. So that gives us resistance, again, in ohms. There's a table in your book, Table 2.1, that shows the resistivity of some common materials. And so from that, we can calculate Ohm's Law. So remember we talked about the, I just lost my train of thought. We did power. Passive sign convention, there it is. I knew it would come. So the passive sign convention, we use that here as well for Ohm's Law. So if I have, again, some dummy block of material. So I looked at this when we were doing P equals VI. And I have a voltage V. And I have a current going this way, I, and this is R. Then I have V equals positive IR. If I switch the direction of that current, I'm drawing the same picture here. I'm switching my current, so saying it's going this way. This gives me V equals minus IR. It's really important to pay attention to that. If you get that wrong, then it's going to mess up your entire problem. So that is, again, 2.2 Ohm's Law. Most resistors will have a specific value. You can go from 0 to infinity. So think about what zero resistance would mean. Zero resistance, no resistance. Anything can get through. So zero resistance is equivalent to a short circuit. R equals 0, we call that a short circuit. So it's just a wire. There's no resistance here. Current can go flying through all at once. We can have a resistance of infinity. What's that mean? Infinite resistance. Nothing's ever going to get through. If it's never going to get through, well, then we need a big old hole. So if we have a big old hole, we know that current cannot get through there. And we call this an open circuit. I should have written that down up top. So this is an open circuit, and this is a short circuit. So we'll work some example problems in a different video. And I want to look at section 2.3 real quick in this video as well. Section 2.3. Section 2.3 is really just terminology. It's on nodes, branches, and loops. So a branch is a single circuit element. That means anything in your circuit. So if I have some circuit with a battery, let's say a resistor, and we haven't seen any of these yet, but let's just draw a capacitor. Doesn't matter what I draw. I have 1, 2, 3. I have 3 things. So I have 3 branches. A node is a point of connection between 2 or more elements. So right here, I have 2 meeting. I have 2 elements meeting here. I have 2 elements meeting here. So I have 3 nodes. And a loop is any closed path in a circuit. This one has 1 loop. So let's look at another one real quick here. This marker's trying to die on me here. I don't want to do that. Let's put another resistor in here. Squeaky, squeaky. So let's think about branches, nodes, and loops. How many branches do I have? Again, branches is just stuff. How much stuff is in your circuit? 1, 2, 3, 4. 4 branches. How many nodes do I have? Node is a point of connection between 2 or more branches. Well, I have lots of things that connect here, right? I've got 1, 2, 3. So there's one node. Got some stuff meeting up here. That's our second node. And then 1, 2, 3 meeting down here. That's my third node. Loops. How many loops do I have? I have 1. I have 2. Any closed path. So I also have the one that makes this outside. So I have 3 loops. So when we talk about loops, we can have loops and independent loops. So an independent loop doesn't contain any other loops. So here I have 2 independent loops and 1 just regular loop. So it would be 2 independent loops. The other thing in section 2.3 is on series and parallel. I think I can get that on here. So series is when elements in a circuit exclusively share a node. So these 2 right here are the only things connected at this node. That means these 2 are in series. These 2 exclusively share this node. Nobody else is connected there. So those 2 are in series. If we look at this one, it's getting a little messy down here, but we've got series right here. These 2 exclusively share that node. At this node, there's 3 things there. So there's no exclusive sharing. Right there, all 3 are sharing that node. So that is not, these 3 are not in series. Same thing down here. There's 3, so they're not in series. Up here, there's 2, so we can say those 2 are in series. So here's all my series in pink. Our other one that we want to look at is parallel. Elements are in parallel if they share the same 2 nodes, regardless of what else is connected there. We don't care, but as long as they share the same 2 nodes. So of these 2 circuits, we only have one parallel relationship. Right here, these 2 are in parallel. They both share this node, they both share this node. So those 2 are in parallel. So I'm going to say it one more time. Series, they must exclusively share a node. Means you can only have 2 things there. Parallel, they have to share the same 2 nodes. This wraps up section 2.2 and 2.3. You can watch the next video for example problems.